compounds that are non-electrolytes are mainly compounds that don't dissolve in the first place. So remember, if you don't have a compound that dissolves, then it can't dissociate. Dissolution or dissolving in water is a prerequisite to being able to dissociate. Not everything that dissolves dissociates, but everything that dissociates also has to be able to dissolve. Okay, so that's kind of how you can predict whether something should be in one of those three categories. Let's go back to our assignment here, and I want to talk a little bit about how to fill out this table. So as you can see, conductivity values have been provided here, and again, these values don't really mean much on their own. You kind of need to compare them to each other. So what do I mean by that? If we look at our first row here, distilled water, that has a provided conductivity of 16 microsiemens per centimeter, which, what does that mean? Is that high? Is that low? Well, if you kind of take a look at some of these solutions down here, like say sodium hydroxide, 0.5 molar sodium hydroxide, which as you know is a strong base, that is about 300? Yeah, about 300 times larger than the conductivity value for distilled water. So in relative terms, the distilled water conductivity value there is basically really close to zero. So as you might predict, that is essentially non-conductive. Now, based on a couple of factors, we can go from our conductivity values here to electrolyte class. So if we have a strongly conductive solution, then that means there's a lot of ions present, so we're going to have a strong electrolyte. If we have a conductive but less conductive solution than, say, a really strongly conducting one, then we should have a weak electrolyte. Now, one thing to kind of keep in mind here is what constitutes a conductive but less so than a strong electrolyte solution. And for that, you can kind of apply your knowledge. So what do I mean by that? If we go back to our weak electrolytes here, you can see weak acids, and I also mentioned ammonia as an example of a weak electrolyte. So in fact, if we look at ammonia here, you can see that is a weak base, so we would expect that to be a weak electrolyte. Likewise for, say, acetic acid or vinegar, which is just another type of solution of acetic acid. These all have conductivities that are over 1,000, so somewhere around, say, 1,200 to 1,600. And that's quite a bit higher than something like, say, distilled water or even tap water, but it's still about 3 times smaller than, say, sodium hydroxide or our sodium chloride down here. And so the interpretation of those values is that they are significantly conductive, but still considerably less so than a known strong electrolyte. So that's something that can help you figure that out. As we kind of go down this table, I want to point out a couple of things, and some of these might be less obvious, especially if you've not taken these measurements yourself. So in particular, I want to point out the discrepancies in these last 4 rows down here. So all 4 of these at your first glance are sodium chloride, and indeed they all contain sodium chloride. But notice both the concentration and the states of matter here. So this first one is sodium chloride solid. That's not a saltwater solution. That's literally taking a conductivity probe and sticking it into solid, like rock salt or something. And you can see here that the conductivity there is pretty low. So remember, to have a conductive solution, you need to have dissociated ions. In the solid, so just solid sodium chloride, no water around, those ions are just stuck together. They're not dissociated. So that's something you need to kind of take into account in interpreting that result. Another thing to take into account, and this is kind of underscored by the fact that we have 3 different concentrations of sodium chloride in these last 3 blanks. 1 molar, 0.001 molar, and then 10 to the minus 6 molar. So just to kind of clarify the relationship between these, 0.001 molar is 1,000 times less concentrated than 1 molar, and this last one here, this 10 to the minus 6 molar, that's 1,000 times less concentrated than the previous one, and 1,000,000 times less concentrated than the 1 molar sodium chloride solution. Now, when we're measuring the conductivity, we're not directly measuring the electrolyte class. So conductivity itself really only tells you what the concentration of ions in solution is. Now, what determines concentration of ions in solution is two factors. One is the electrolyte class, so if we have a high concentration of ions, then we pretty much automatically have a strong electrolyte. But another thing that determines it is the concentration of the solute to begin with. So we can see here, for instance, that with our 10 to the minus 6 molar sodium chloride, which is a really low concentration, that has a conductivity of 220. That's a lot less than something like even some of our known weak electrolytes. So does that mean that sodium chloride is a weak electrolyte at lower concentrations? No. So all of the sodium chloride that's in that solution is completely dissociated, so it's a strong electrolyte. It's basically 100% dissociated. There's just so little of it to begin with available to split up into ions that the overall conductivity is going to be low, even though it's going to be fully dissociated. So that's something that you need to take into account. And so your conductivity and basically the concentration of ions relatively, so none, fewer, many, is determined by both electrolyte class and the initial concentration of whatever the solute is. For most of these things where you have a dissolved substance, most of these are 0.5 molar, especially early on in this table, but then you can see the effect of varying the concentration of the same substance in these last three, which are all sodium chloride. So what you're going to do is fill out this table here and use those results to kind of organize things in the post-lab questions and give explanations for any of your classifications and evaluate this statement down here based on your results. So that about covers what I need you to do for this exercise. So again, just keep in mind you'll have the week of the 6th through the 10th to work on this, and it'll be due at the end of the day on the 10th at the latest. Of course, you can always turn it in to me earlier. So the way you can do that, of course, is just email the file back to me after you've made changes and rename the file so that your name is in it. And you can go ahead and turn that in. I'll get those graded once everybody's turned them in, and I'll post those grades on D2L, and you can contact me if you have any questions. And of course, if you have any questions while you're going through this procedure, I would definitely recommend that you reach out to me. So again, I'm always available by email, especially now that we're doing all online instruction. And if you look on the course D2L page, there are details there on how to reach me for virtual office hours. So on Microsoft Teams, which you should all have access to via your UNG email account, even if you have to, say, download the Teams program on your personal computer or whatever, you can follow the instructions on D2L to find my Teams page for virtual office hours, and you can use that to ask me questions either just sort of in a chat format, or really I would encourage you to actually engage with me. I do have a laptop camera and everything that I can use to talk through things with you if you have any questions. So this is all we're going to do for now for 1211 lab. I'll come back at you soon with the second exercise, which I'm not sure exactly what that will be yet, but I will make sure to keep you all on the loop with that.